Houston and Esther are listening in on this later. There was a question about the first test. That was chapter 5. No, I'm sorry. I've been saying 5. That was my other class. This was chapter 8 test. Yes. Test 1, chapter 8 test, test 1. There was an issue with that. At least one student, when he opened the test was not all there. Portions of it were and portions of it weren't. I think part of it may be the fact that Word has changed, and Word aggravates the fool out of me on this. They will update versions of things and make them incompatible with the previous versions, and that to me is completely irresponsible. Okay, WordPerfect, which I used for years before I ever had to start using Word, always on their upgrades made sure they could, the previous versions, it was seamless. Okay, always was seamless. Word was not. Word wanted you to buy the new version every time, and that may be the issue. The other issue may be that Blackboard screwed it up, because Kyle had opened it through the week 4 activities, and Jesus has opened it through the message. Jesus was able to read his, Kyle wasn't able to read his. So it could be that Blackboard screwed it up. That's not at all surprising either. So anyway, sad song. Any other questions, issues, concerns, anything that I can address now? And Kyle, sorry I didn't see the email over the weekend. I could have gotten something done then, but you still are isolated until Thursday. So I didn't lose you but a day or two maybe. All right. Okay. So any other questions, issues, concerns before we get started today? Last time we were at the end of 9.2. Chapter 9 is infinite series, and 9.2 is series and convergence. And we had done everything in 9.2 that we were going to do except for the last problem, which is an applied problem. And this applied problem, example 6, is not on the slide set. A ball is dropped from a height of 6 feet. Okay? Now I'm going to try to kind of draw a little picture of this. Okay? Here will be supposedly the floor. That's supposed to be a level floor. And it's dropped from a height of 6 feet. Okay? So this is 6 feet high. Okay? Height of 6 feet, and begins bouncing. So the ball is dropped from here, not thrown, dropped. Initial velocity 0, just released from rest. Dropped from 6 feet, begins bouncing as shown in the figure. So here's the figure. I'm not going to be able to draw it as nicely as there, so I'm going to let you see it for those who don't have books handy. If I can hold this book in such a way you can see it. There it is. Okay, there's the figure. The ball is dropped up here from 6 feet. It goes down here and bounces. Now they're giving a little bit of a horizontal motion. There really isn't, but it's just showing you the bounces. The first bounce goes up and then down and up and down and down. If you've ever, dropped any kind of somewhat elastic ball, you know that it does this. There's always some energy loss. It doesn't always come back to the same height as you did. Now, when you're dribbling a basketball, you're pushing the ball down every time you dribble, and that means it's going to come back up to your hand. If you were just releasing it and held your hand there waiting for it to come back, it's not going to make it. Okay? So, that was the figure. I'm going to try to do that. The height of each bounce is 3/4 of the height of the previous bounce. Okay? So, this falls from 6 feet. Okay? Falls down to the floor and bounces back up. It says 3/4, right? 3/4. can't find it. Yeah, 3/4 of the height. So 3/4 of 6, that would be 9/2, I think it is. So it bounces back up to 9/2, which would be 4.5 feet. Okay, and then it drops from there 9/2 and bounces back up 3/4, which would be 27/8, I believe it is. Okay, and drops from there 27/8 and bounces back up whatever 3/4 of that is, drops from there and bounces up and continues this. Okay, it continues it technically infinitely, but you know real balls don't do that either, but they do come close. Okay, now the height of each bounce is 3/4 of the height of the previous bounce. Find the total vertical distance traveled by the ball. Okay, well, let's just list those. Okay, it would be 6 feet plus 2 times, because you see it goes up and down, 3/4 of 6 feet plus, and then it goes up and down again, and that is 2 times 3/4 of 3/4, so I'm going to make that 3/4 squared of 6 feet. Okay, and it continues that indefinitely. Okay, so let's see if we can figure out what that is. Well, it's 6 to begin with, plus, okay, this is going to be a 12. 2 times 6 is 12. 12 times 3/4. See, every one of these will have that 12 in it. Okay, 3/4 to the nth power. Okay, here n is 1, 2, 3, 4, and so forth to the nth. So there's our infinite series. Okay, so you can express that as, and this, by the way, is a geometric series. Okay, so it's 6 plus, now I was just going to see if they do it the smart way. I think they will. They're going to factor the 12 out. Okay, I was going to say I hope they do that. Okay, and then what you would have left then, since you have 12 times this n equal 1 to infinity of 3/4 to the nth. Okay, now for some reason they say n equals 0 to the n plus 1. I see absolutely no reason to do it that way. I'm trying to see if there's any reason in the world to do that, and I can't see any. So let's just go from there. Okay, now this is, if you turn back a few pages, it is a geometric series, and that would be on page 601, convergence of a geometric series. Your A here is 1. You could have left the 12 in there, but there's no reason for it. I see. Geometric series does start with n equals 0. Okay. Okay. So that's why they did it. I had forgotten that. Do all geometric series always do that? I guess they do. So that's why they had to do that. So they pull the 1 3/4 out and make it to the 0. Because if you pull one of them out, the first one out, it still doesn't seem like it should make any difference. But that's why they do 6 plus 12 times 3/4 is 9. Okay? Times the summation of n equal 0 to infinity. Okay? Of 3/4 to the nth power. Okay? Now, this will be 6 plus 9. Now, so I'll turn back to see that. Here your A is 1. Okay? Your R is 3/4. Okay? So this will be 1 over okay, I was trying to think why they have a prime there. They don't. That's a comma. That is 1/4. 1 minus 1/4 is 1 minus 3/4 is 1/4. Okay. And that works anytime your R is less than 1, which it is. So this will be 6 plus 9 times 1 divided by 1/4 is 1 divided by 1 over 4, which is 1 times 4 over 1, so times 4, and this would be 6 plus 36 equal 42 feet. Okay, that's what I got, and that's what they got. Okay, sorry about that. I had forgotten geometric series start with n equals 0, not n equal 1. Okay, so, but that gives us their answer there. That finishes. Any questions on that? It's a fairly straightforward problem. It is a bit bizarre, but you have to get all the pieces in place but able to do it. If there are no questions, remember the concept checks are good things to look at. I usually don't say much about them, but they are good things to look at, especially if you're trying to get in your basically the concepts down before you start working on the exercises. But once you start on the exercises, any of the odds 5 through 9, they're all at Calc Chat. 11 through 17, they're all at Calc Chat. 11's at Calc View. 19 through 23, the odds 19 to 23, they're all at Calc Chat. 19's at Calc View. 25 or 27, both at Calc Chat. 29 to 37, all at Calc Chat. 33's at Calc View. The odds 39 to 43, all at Calc Chat. 39's at Calc View. 45 to 57, they're all at Calc Chat. 47's at Calc View. 59, you can explore doing that if you'd like. That should be at Calc Chat. The odds 61 through 65 should be at Calc Chat. 67 says you'll need a graphing calculator or some type of device, graphing utility. See if you can do it without it, but 67 should be at Calc Chat. 69 should be at Calc Chat. They say you may need that one as well. Then any of the odds 71 through 75, they should all be at Calc Chat. 77 should be at Calc Chat. 79, any of the odds 79 through 81, or 79 or 81 should be at Calc Chat. 83 and 85 should be at Calc Chat. 87 through 89 should be at Calc Chat. 87 or 89 should be at Calc Chat. And then you have some true false. 91 to 95 should be at Calc Chat. And then any of the odds 97, they don't have enough of these, do they? 97 through 101 should be at Calc Chat. All right. Any questions? Now, Let me say this before we move on. I wish we had time. I would at least take you through a slideshow of 9.3. These are two tests that you can make to see if your series converge or not. Okay. The first of these is the integral test. We have sort of talked about that one before, how you replace the series with an function and then integrate the function rather than summing the series. And that's the integral test. But then the P convergence test, it kind of goes back to something sort of like the geometric series. It's not quite the same, but like the geometric series, and it tells you whether a series converges or not depending on the value for the power. That's what the P stands for. 911 is the theorem that explains that one. That's in 9.3. 9.4 talks about comparisons of series, and this is called the direct comparison test. It's kind of like the old squeeze theorem. So you can, if you think in your future you may have to be doing infinite series. I don't know what your majors are. I don't know what the likelihood of that is. If you're mostly engineers, I don't know that many of the engineers do that, but if some of you are math majors or perhaps some other major that you might want to take a look at these. And that's one reason I'm skipping them, because I don't think there's a lot of you that probably going to need this. There's a limit comparison test. There's the direct comparison test, is theorem 912, and theorem 913 is the limit comparison test. These are both in 9.4. Okay. 9.5 is alternating series, which is another type, and theorem 914 gives you the alternating series test. And then also 915, theorem 915, the alternating series remainder, which sometimes is useful to know or not. Then there's the absolute convergence test. We talked about this a little bit in, I believe it was sequences. It may have been series, but there's theorem 916 with that one, with some definitions at the bottom of page 626. Then 9.6, if this isn't enough, here's the ratio and the root tests. Okay, ratio test is theorem 917, and the root test is theorem 918. There's also guidelines for testing a series for convergence and divergence that sort of summarizes several of those. And then there's a summary on page 636. Maybe that's all you need, is notice those. But that's not all. 9.7 introduces you to a set of polynomials called Taylor polynomials. Okay. And in this you'll see a little blurb on Brooke Taylor, the guy that was that this is named after. He wasn't the first to seek polynomial approximation of transcendental functions, but his account was published, was one of the first comprehensive works on the subject. So again, it named it after the guy who published it, even though he wasn't the one who probably came up with it. Rather a strange looking dude in my mind. Okay. And then there's the Maclaurin test, named after a scholar, Maclaurin polynomial, named after Colin Maclaurin, a Scottish mathematician, very closely related to the Taylor polynomials. Of course, Maclaurin was born he was born during the lifetime of Taylor. Whether they actually interacted, I kind of doubt, because of the difference in ages, but they were around the same time. But anyway, Those polynomials are very famous. Theorem 919 is Taylor's theorem, and that's in 9.7. 9.8 talks in general about power series, which are used in a lot of applications. So by all means, if you think you may be using them, this may be the type that you'll be using. There's definition of power series there on page 651. Then theorem 920 on 652 tells you the convergence of a power series. Okay. James Gregory is mentioned in that section, along with theorem 921, properties of functions defined by power series. Okay, so Maclaurin and Taylor series were power series that were used to represent transcendental functions. These are power series on their own basis. And then 19.9 is representation of functions by power series. They mentioned Joseph Fourier here, French mathematician. In that is also mentioned Cauchy, Dirichlet. So several names there. Potential paper topics, hint, hint. I hope you're working on your papers. Operations with power series are given 663. This is one really long chapter. That's why we're skipping most of it. Famous Indian mathematician, I can't come close to pronouncing his name, Srinivasa Ramanujan, I guess is how you say it. He did a lot of work with those too, and there's another potential paper topic. And then you thought you were through with it, but no, you weren't. Now they talk about Taylor and Maclaurin series as opposed to the polynomials. Now, of course, there's links between them, really strong links. But these are power series that we were talking about in the two intervening sections, but they're the ones that were used by Taylor and Maclaurin. These are their series. And theorem 922 is there. The blurb on Maclaurin is mentioned here. Definition of Taylor and Maclaurin series, theorem 923, convergence of Taylor series, and then guidelines for finding Taylor series. And then they introduce in the same section binomial series, which is another really famous and often used series. Okay, so that's worth a look. I wish we had time to go over all these. We don't. And then the power series for several of your elementary functions: 1 over x, 1 over 1 plus x, log x, e to the x, sine x, cosine x, arctangent x or arcsine x, and then some more powers. These are given there in section 910. And I think that finally finishes, yes, chapter 9. We don't have time for that. Sorry, we don't. Then begins chapter 10, conics, parametric equations, and polar coordinates. We're not going to do conics, that's 10.1. We're going to start with plane curves and parametric equations, 10.2. The reason is these conics were not listed in your course description. There will be a time at the end of the next chapter, if we get there, that I will go back and give you a quick and dirty review of the conics. But we're going to begin with 10.2 and go from here. We're only going to do 10.2, 10.3, and 10.4. We will do polar coordinates and polar graphs, but we're not going to do area and arc length in polar coordinates, nor the polar coordinates for conics and Kepler's laws. So we're only doing 10.2, 10.3, and 10.4. So this book is heavy. Your next test will be 9.1, 9.2, 10.2, 10.3, and 10.4. 5 sections. We've got 2 of them done. We're starting the third one today. Conics and calculus is how this, no, I'm sorry. We're skipping conic. Oh, and by the way, under conics, you see several other potential paper topics. Hypatia, the Greeks discovered conic sections, and she was just an incredible woman. She was a brilliant mathematician way back before women were even supposed to have any education whatsoever. Okay, Nicholas Copernicus, you probably heard of him in astronomy senses. He was also quite a good mathematician. He used conic sections. So there's several paper topic possibilities here. Seems like there's one more. Carolyn Herschel, first woman to be credited with detecting a new comet. She was English astronomer Caroline Herschel. Okay, and she actually discovered a total of 8 new comets. And again, big connection between astronomy and conic sections. Let me put it that way. That was 10.1. It's worth looking at some of these sections we're skipping for the idea of paper topics and things like this. So let's get started in 10.2. Okay, so let me pull back up any questions before we get started in 10.2? Okay. So let's get started from the current slide. And chapter 10 is entitled Conics, which we're not doing, Parametric Equations, which we are doing, and a little bit in polar coordinates. We're not going to do everything in polar coordinates, but we will do a little something. Okay? The main thing here is parametric equations, and that's where 10.2 begins. So 10.2, plane curves and parametric equations. Now this doesn't mean curves that aren't fancy. Okay, that's not the plane. This is not PLAIN. This is curves within a plane, a two-dimensional sheet. That's the plane we're talking about here. Not an airplane, but a two-dimensional thing. The XY plane, the YZ plane, the XZ plane, whatever plane you're in, curves within that plane. And we'll be talking about parametric equations too. That's a whole new set of definitions here. So our objectives here are to sketch the graph of a curve given by a set of parametric equations. Now we haven't talked about what they are yet. They're pretty simple. We'll eliminate the parameter, which is where the parametric equations get their name, in a set of parametric equations, and finally wound up with just a XY type situation. Okay, we'll find a set of parametric equations to represent a curve. Now notice the difference here. Objective number 1, we'll sketch the graph of a curve given by the parametric equations. Number 3 here, we'll find the parametric equations that represent a given curve. Here we start with the equations, you graph the curve. Here we start with the curve, you find the equations. And then finally, it says understand 2 classic calculus problems, the tautochrome and brachistochrome problems. Now, when I was doing the stuff I was doing today to get this on, I decided let's skip that part because we really need to move on. I'll give you a quick and dirty on it, but you're not going to be responsible for doing any of those. So that's it for this one. So basically that fourth objective I'm going to eliminate. Okay, I will introduce you to it, but we'll stop. So let's start. Consider the path followed by an object that's propelled into the air at an angle of 45 degrees. This could be Kyle hitting that ball that he's hoping going to be a home run. That would be the optimum angle for him to hit that at 45 degrees to get the maximum distance. We haven't gotten there yet, but we'll see that. For an initial velocity of the object of 48 feet per second, Kyle, that may not do it. I don't know. We'll see. The object travels the parabolic path given by this rectangular equation. Y is equal to minus x squared over 72. Oh my goodness, where did that come from? Plus x. Okay. Now, what in the world is your x here? Okay. Here is your thing. You're starting this off from the point 0, 0, leaving that point at 45 degrees here, going up, reaching a maximum and coming back down. That's a parabola illustrated by this. Now, nope, that's not going to do it because that's only going to travel a total of 72 feet, it says. Don't think any of your ballparks have fences that short, okay? So, where did this come from? Here's where it came from. X is equal to 24 times the square root of 2t. Okay? Now, what in the world did that come from? Well, remember the initial velocity was 48 feet per second. That was at an angle of 45 degrees. Well, the x-coordinate of that is 48. 48 is the hypotenuse. The x-coordinate of that is 1 over pi halves, 1 over the square root of 2 of that, because the cosine of 45 degrees is root 2 over 2. Okay? So, take the 48, multiply it by root 2 over 2. The denominator 2 divides into that and gives you 24, and you have a root 2 left in the numerator. So this is your x component of that velocity, okay? And that doesn't change, because if you hit it at that angle here, the x component does not change, because the only thing acting on the ball after it leaves your bat or racket or golf club or whatever is hitting it with, whatever after it leaves contact with that, the only force on it is gravity pulling downward. So this horizontal component is going to be constant throughout its flight. So that's why it's 24 root 2 times t. Now, you don't need to know all this, but for those of you who have taken your physics already, you probably recognize that. Now, your vertical component, the y component, is going to be 1/2 acceleration due to gravity squared. Well, acceleration due to gravity in feet per second squared is 32 feet per second squared. 1/2 of that is 16, and negative because gravity is always pulling downward. So there's your first component of your gravity pulling downward. Your initial, since it's 45 degrees up, your initial velocity there was the same as your initial velocity in the horizontal direction, because 45 degrees, the sine of 45 is also root 2 over 2, so this gives you your initial velocity in the y direction, and this is the acceleration due to that anytime after that. So, these two equations from physics, when you combine them together, that gives you this motion here. Now, it's not clear how you come up with that. It is quite doable, but that's what they're going to talk about later. But I see no reason not to do it now. So let's go on and do it. The easy thing to do here then, if I can get my pen to show up somewhere on the page, there it is, okay, is solve this equation for t. Okay, now how am I going to do that? I'm going to divide by 24 root 2, which, if you don't like radicals, it will be 2 or square root of 2 divided by 48. Okay, so from this you get t is equal to the square root of 2 divided by 48. Okay, just divide this, both sides of, I'm sorry, and this is times x. Okay, you're dividing both sides of this equation by 24, that would have been a 24 here. Dividing by root 2 would have had a root 2 down here, but if you multiply numerator and denominator by root 2, you get a root 2 up here, and you get a 2 here. 2 times 24 is 48. So that gives you that. Take that value for t and plug it in here. So y is equal to minus 16 times, now I'm going to square this. That will give me a 2 in the numerator. This will give me a 48 squared in the denominator, which I don't really care for too much. I'll write it down. 2 and 48 squared. I'm going to write that down in pretty much close to factored form. That would be 4 times 12, okay, that's 48. We're going to square that, so that would be 4 squared times 12 squared, okay. So there I've factored it, and we also have the x squared, okay, because that's what t is, okay, plus 24 root 2 times the t, which is root 2 over 48, so that basically is 1/2 x, because you had the x there. Alright, so let's see what we've got then. Y is equal to, now, the one reason I did this, and I had squared that, but it disappeared then, and it's still going to disappear again. But 4 squared is 16, so this wipes that out. And 12 squared is 144, right? And half of that, because the 2 will go in 144, 72 times. So there we have our minus x squared over 72. Okay? And then here we have I sort of messed this one up, I think. T is equal to, okay, let's go back to the first way of expressing that, is 1 over 24 root 2 x, okay. I did it this way, and then when you put t is equal 1 over 24 root 2 x, the 1 over 24, yeah, these go away. So I messed up having that 2 down there. It's not there. I forgot to take that out. So that's where you get your plus x. It's just x. Okay, that's where they got this. Now that's jumping way ahead, but that's where that equation came from. It came from these two equations that you can get exactly from physics. This comes from the fact that you had a 45-degree angle here as your initial velocity. That came from the same fact. This is the acceleration due to gravity. This is the velocity in the x direction, initial velocity in the y direction, and this is the acceleration, the distance influenced by the acceleration due to gravity. So there's where you came from. Now, in 1 second, where t is equal to 1, this will be 24 root 2 over 24 root 2. This will be minus 16 plus 24 root 2. And that gives you a height up here of something pretty close to 18. I haven't figured out to see what it is, but it's only something like 36 feet into the flight before it reaches its maximum height, and then it comes back to ground level at 72 feet. Nope. What would that be? Short Outfield, I can't remember what the base paths are. They're around 36 or so. So this would be short outfield. Probably caught that one, Kyle. Sorry. Okay. Now, to determine this time, okay. See, they've already done it for you here, so they seem like they're going backwards here. To determine this time, you introduce a third variable, t, called the parameter. By writing both the x and the y as functions of t, we obtain this. Now, I don't know. This is a little bizarre here. They've shown this. They drew the curve here. This is y versus x here. Drew the curve, did this, and then they gave you parametric equations, and now they're telling you where you got it. Now this is called the rectangular equation. That's in x and y. The parametric equations are those that have the parameter t. Okay? So to determine the time, introduce that third variable t, called the parameter. By writing both x and y as functions of t, you obtain these two parametric equations. Okay. Now, I did it from a physics viewpoint. I'm not sure how they're doing it. Maybe they're doing it from a purely mathematical viewpoint, but we've already talked about where they come from. From that set of equations, you can determine that at time t equals 0, the object's at 0, 0. Because put t equals 0 here, that's right when you hit the ball. Well, wrong one. Yeah, here. T equals 0 here, your x is 0. T equals 0 here, that's a 0, that's a 0. Minus 0 plus 0 is 0. So yeah, you're at the origin, and that's why they drew it there. And similarly, at time t equal 1, the object was at the point 24 root 2, that's the x component, and 24 root 2 minus 16, that's the y component. And for this particular motion problem, x and y are continuous functions of t. The resulting path is a plane curve. Okay? Happens to be a parabola, but for now we're just calling it a plane curve. So here's the definition of a plane curve. This is P-L-A-N-E, meaning the curve on a two-dimensional surface. Plane curve, the plane. If f and g are continuous functions of some variable t, t doesn't have to be time, but that's what we've been using in that first example, but any parameter t or s, you can name it anything you want to, on some interval I, then the equations x equal f of t and y equal g of t, these are functions of the independent variable t. See, x and y here are both dependent variables. These are parametric equations. T is called the parameter. The set of points x, y obtained as t varies over the interval I, and I is an interval in t, by the way. T is in the interval I. Is called the graph of the parametric equations. Taken together, the parametric equations and the graph are called a plane curve, and that's denoted by the symbol capital C. Not to be confused with the constant after an integration. This is just the plane curve represented by those parametric equations. Now, when sketching a curve represented by a set of parametric equations, I'm having trouble talking. Excuse me just a minute. I did a bunch of yard work this weekend. That's why I didn't have but limited time to do that 6 hours of wasted effort that I did on those reviews. But did some yard work, and I think all the fall stuff is in the air. So I'm sort of congested. Sorry about that. By plotting the resulting points, let's see, let me go back and make sure. When sketching the curve representing a parametric equation, you can plot the points in the xy plane. For each set of coordinates, x and y are determined from the value chosen for the parameter t. Now let's go back and see. Pick a t, any t equals 3. Plug that in, you get a value for x when t is 3. Plug that same value, 3, in for t, you get the y value when t is equal to 3. That new xy pair gives you the point that you're at when t is equal to 3. Pick another time, and these are continuous functions, so there will be something. You get another x value, you get another y value, plot those, and you're at the next point. Generally, you can connect the points with the plane curve C. Okay, so each set of coordinates x, y is determined from a value chosen for the parameter t. A single value at the same moment, calculate the x and calculate the y. That gives you a point on the curve. At a different t, calculate the x, calculate the y. That gives you a different point on the curve. By plotting the resulting graphs in order of increasing values of t, the curve is traced in a specific direction. That is called the orientation of the curve. Now the one we have back here, of course, is going from 0, 0. If I can get my pen to show up. Where are you, pen? There you are. This is direct, and there's the arrow indicating the direction. It's going from here to there. Not all curves will be going that way. It may look like they would be. Certainly if you hit a ball, that's the way it's going. Okay. But that's the orientation of the curve. So here's example 1, which you find on page 701. Okay. Sketch the curve described by the parametric equations. X of t is f of t. X is f of t, and that's defined as t squared minus 4. Y is this g of t, which is g divided by 2, t divided by 2, where you're going to let your t go from negative 2 to 3. Now it'll be every value of t in between here. We can't calculate all of them because there's an infinite number of t's between minus 2 and 3. In fact, there's an infinite number of t's between minus 2 and minus 1. You can't calculate them all, so let's just choose the integers and see what happens. Okay, so here's how I like to do it. You don't have to do it this way, but here's how I like to. I like to put, remember when you're graphing functions, you usually did a t-table, didn't you? Something like that. You did x's and y's, calculate y is some function of x, calculate what give me an x, calculate a y. Well, this time it's going to be a 3-tier table. Give me the t first, and then I'll calculate the x, which by the way is f of t, and then I'll calculate the y, which by the way is g of t. Okay, so what I'm going to do here, maybe you could call this a t-table too. It's got t in it, doesn't it? So let's let t equal negative 2. When you plug that in here for x, you get 4 minus 4 is 0. Plug it in for y, and you get a minus 1. Let's do t equal minus 1. Here you get a negative 3. Here you get a negative 3 halves. Okay, let's do t equal 0. Okay, t equals 0. This will be a minus 4. This will be a 0. How did I get minus 3 halves? When t is equal to minus 1, this will be a minus 1 half. So sorry about that. I was just looking at that and said, that's not anywhere close to right. I used the 3 from here, not the 1. Okay, let's do t equal 1. T equal 1, this will be minus 3 again. This will be positive 1/2. T is equal to 2. This will be 0 again, and this will be 1, positive 1. And then we'll do t equal 3. This will be 5. And this one will be 3/2. All right, let's see if we can plot these on the XY coordinates. Okay, I don't know where, there it is. Okay, let's see if I can make up. This is not very pretty. So X is going from 0 to, from -4 to 5. So let's do -1, 2, 3, and 4, positive 1, 2, 3, 4, and 5. I said X and I plotted those on Y. I don't know where, something's wrong with the old gray cells today. There's your 1, 2, 3, 4, 5, -1, 2, 3, and 4. Okay. The Y's aren't getting anywhere near that big. Okay, so let's do them. X equals 0, Y is equal to -1. Right there. Okay. X equal -3, Y is equal to -1/2. -3 would be here, -1/2 would be right about there. X equal -4, Y is equal to 0. Quit doing that. This is such a pain in the neck. I don't know where my cursor's gone. There's something about this Wacom board. Oh, I know what the problem was. I had it too close to the screen. Okay. It erased everything. T, X, Y. -2, -1, 0, 1, 2, and 3. X is, where are you, pen? There you are. Okay. When t is -2, this is 0. When t is -1, this is -3. When t is 0, this is -4. When t is 1, this is -3. When t is 2, this is 0. And when t is 3, that's 9. The Y is, t is -2, Y is -1. T is -1, Y is -1/2. T is 0, this is 0, 1/2, 1, and 3/2. Okay. Now let's see if we can plot those. Okay. X is going out to 5. 1, 2, 3, 4, 5. And back here to -4. My throat's going on me, sorry. And Y is basically going from 1, 2, and -1. That's all we got for Y. So 0 -1, this is where it messed up before. 0 -1 is there. -3 -1/2 is right there. -4, 0 is right there. -3 positive 1/2 is right there. Get out of there. Okay. And 0, 1 is there. And 5 and 1/2 is right about there. Okay. This is a parabola, sleeping parabola, that does something like that. Now this is as far as it goes. They don't give us anything beyond that. This is the domain for t. It's not the domain for x, okay? T is the independent variable. And this, since it's going in that direction, we would put our arrow, our orientation, if I could get my pen to show back up. Where are you, pen? There it is. Okay. This is the direction it's going. From here to there to there. Okay. Stopping there. It doesn't go any beyond it. Didn't come anywhere before it. Now, looking at that, you see y is not a function of x, but we don't pretend that it is. This is a curve. That's your plane curve. It doesn't have to be functional, a function in x and y. It is a function in t. X is a function of t, y is a function of t. Those are perfectly legitimate functions. When you plot it like this, you see that y is not a function of x, nor, well, actually, x is a function of y. So that's rather bizarre, but it certainly can be shown that's the case too. And that, in fact, we could do that. So we have now done example 1. Sketch the curve described by those parametric equations. Okay? And you're limited here to -2 being less than or equal to t less than or equal to 3. Now, that's why I tried to draw a continuous curve here. I sort of messed up there, but it's hard to draw with this thing. That's a smooth continuous curve. That is your curve of the parametric equations. Now, here's theirs. They did theirs horizontally. I like to do mine vertically because I sort of grew up that way. And you pick the t's, -2, -1, 0, 1, 2, and 3, just like we did. And then calculate the x's, calculate the y's, and then plug them in. And there is, you have it. And you see the function is going from the, when t is equal to 0 here, to t is equal to 3 there. By plotting those points in order of increasing values of t and using the continuity of f and t, then you can connect the dots and you obtain the curve C shown here. Notice that the arrows on the curve indicate its orientation as t increases from -2 to 3. There's no way you can just look at a set of parametric equations and tell its orientation automatically from the top. So don't pretend that you can. Now, that was page 701. Moving to 702, we're going to eliminate the parameter. Now, I've already done this for you once, and we're going to do it with those that we were just using. Finding a rectangular equation that represents the graph of a set of parametric equations is called eliminating the parameter. Okay? Now, they're not going to do it. They're doing it in the text, but not in the example. Let's go back, and we're going to eliminate the parameter. Okay? And this will be the best place to do it from. Find the simplest expression of t, and that would be this one here. Solve that for t. Well, this would produce t is equal to 2y. Okay? Then take that expression of t and plug it in here. And you have x is equal to 2y squared minus 4. Because it's that t is this t. Okay? So 2y squared plus 4. This will be 4y squared minus 4. Okay? There is your equation. X is a function of y, which is exactly what you have here. Only you're limited to these values for t. You can't really go beyond them. You are limited for that. Nothing in this expression indicates that limitation. You have to realize that that you are stuck between those two. And that, I think, is what they got. Yeah, x is equal to 4y squared minus 4. Okay, once you have eliminated the parameter, let's go on back to my slides. Yeah, there it is. Once you've eliminated the parameter, you can recognize that the equation x equals 4y squared minus 4 represents a parabola with a horizontal axis, not a vertical axis, a horizontal axis, vertex at negative 4, 0. That's this point right here. And shown here, symmetric about the x-axis up to the point 0 here. This part here, t equal from 2 to 3, this part is not mirrored by a part down here. So that is not a, if this had been from negative 3 to 3, then you would have had symmetric about the x-axis. All right, of course I'm getting hungry. The range, what I did, I had a salad in between my last two classes and I wolfed it down too fast. Now my stomach's really hurting, partly for hunger but partly because I ate it too fast and now it's disagreeing with me. The range of x and y implied by the parametric equations may be altered by the change in the rectangular form. Okay, in such instances the domain of the rectangular equation must be adjusted so that its graph matches the graph of the parametric equation. You see, if you were just given this equation right here and told to graph it, that's going to go infinitely long up here and infinitely long down here too. That's not what we have here. We have parametric equations that stopped at t from minus 2 to 3. You can't go any beyond that. So if you are given the xy coordinates, they're called the rectangular equation, you have to specify where the limits are. Okay. Now here's example 2. This is sort of in the middle part of page 702. Okay, we've got about 11 minutes. I think we can get this done. Sketch the curve represented by these equations. Okay, and this is for all t greater than minus 1. Now, that's sort of good because t cannot equal minus 1, because if t was equal to minus 1, there's no problem taking the square root of 0, but you can't have it in the denominator. Okay, so you can't have any t less than minus 1, because then you would have a negative number under a square root. So you can't have either one of them. So this is all t's greater than minus 1. Okay, it says sketch the curve. So again, we set up our t table, you might call it. T here, x here, and y here. This is how I sketch them. You can do it however you want to. And let's start with minus 1, 0, 1, 2, 3. And it keeps on going. It stops here, but it keeps on going there. Okay? What's the x value then? When t, well, it's not equal to minus 1. Okay? So we can't even do that one. I shouldn't have even put that in the table. Oh my goodness. When t is equal to 0, though, you have x equal 1, because 1 over the square root of 0 plus 1, 0 plus 1 is 1, square root of 1 is 1, 1 over 1 is 1. Okay? When t is equal to 1, this would be 1 over root 2, which I'll write as root 2 over 2. Goodness, my stomach's hurting. When t is equal to 2, that would be 1 over root 3, which is root 3 over 3. And when t is equal to 3, I like that one. Square root of 4 is 2. That would be 1/2. Okay. Now I'm going to do the y when y is equal to this, because you can evaluate that. That would be -1. No, you can't. You can't do it there either. So we shouldn't have even put it down here. But let's do it for 0. That would be 0. When it's 1, you'd have 1/2. When it's 2, you get 2/3. When t is 3, you get 3/4. Okay. Where did my pen go? There it is. Okay, let's sort of sketch the graph, because that's what we're asked to do. Now, it looks like to me x's and y are both positive. So let's go this way. And when x is 1, y is 0. So it's right there. Okay. When x is, and root 2 over 2 is 0.707. So it's right here approximately, and you're up at 1/2. So if this is 1, this would be something about right there. Okay, I may not be right on the money, but somewhere close. Okay, when at t equal 3, root 3 over 3. Oh my, let me pull out my calculator. I don't want to do these in my head. I knew 0.707, but I don't know that one. Oh, wrong. Okay, gonna have to turn it sideways to get it to scientific notation, or scientific calculator. And on this one I have to do the 3 first, then take the square root of it, and then divide that by 3. That's 0.577. Okay, and the y is 2/3. Okay, so this is just over 0.5, and this is right at 2/3. Okay, this isn't coming out too nicely. When t is equal to 3, you get 1/2 for x and 3/4 for y. So it looks like to me this is approaching so we got something that's doing like this. Now I can't tell where it's going, but it's doing something like that. Okay, let's see if we can figure out what it's doing. Okay, oh man, I'm hurting. All right, ooh, this is pretty miserable. Here is the simplest, believe it or not, the simplest t here. So let's do this. Root t plus 1 is equal to 1 over x. See what we did? Multiply both sides by root t plus 1, divide both sides by x. Square both sides. Now that's a dangerous thing to do. You have to be careful. That gives us t plus 1 is equal to 1 over x squared. So now we have t is equal to 1 over x squared minus 1. Okay, so that's what we're going to put here. Y is equal to 1 minus x squared minus 1 over x squared minus 1 over 1 over x squared minus 1 plus 1. So these go out. So this gives us 1 over x squared minus 1 over 1 over x squared. Now to me the simplest thing to do is multiply numerator and the denominator by x squared, and this gives you y is equal to 1 minus x squared over 1. So there is what we've got. Y is equal to 1 minus x squared. Sure enough, this is a parabola. That's what it was sort of shaping up to be, but it's only the right side of that. And it only goes down to, well, let's see. Let's see what happens if we continue going up in t. This is getting closer and closer to 1, right? The y value is. You can't ever go negative here, because when t is greater than this is always positive and that's always positive. So you'll never you get closer and closer to the point 0, 1, and that's all you can do. You're approaching that. Okay? Now, because when x equals 0, y is equal to 1. Let's see what would happen if we did a minus 1/2. So I'm going to put that in here, minus 1/2. That's going to be ugly, 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 ugly. So you got 1 minus 1/2 is 1/2. I'll turn it sideways, which I'm going to write as 0.5. And I'll take the square root of that. Okay, and then reciprocate that, 1.414. So this is going to be the x value here, if I could find my thing here. Here it is, 1.414. Okay, the y value is going to be, when t is minus 1/2, it's 0.5, negate that. My calculator, I have to do that. My phone, I have to do that. And then minus 1/2, and that's divided by 0.5, and that's equal to a minus 1. So when your x, so let me put this in. Where is my, can anyone see my pen? There it is. Okay. This would be, what did I say? Minus 1. Minus 1. And the minus disappears. Okay. And then if you take closer and closer to minus 1, like negative 0.9, yes, is it time? It is. Okay, what you'll find, you do get the bottom part of this parabola, and it just keeps on going infinitely less and less and less. Okay, without bound. But it's not going that direction, it's going this direction, because minus 1 is an infinite down here, and it's going up here, but it stops right here, terminates there. And you'll see that's in your book as well. So let me get out of here. Okay. All right, we're going to have to start next time. Oh, let's just go on and progress that. Here is the x. We got that from it, same as we got before. They did it slightly differently, but it's okay. We got that same answer there, and then we got that. Okay. And that became y is equal to 1 minus x squared. But it's only that half of the parabola. It doesn't, I should have drawn the open circle there. It never reaches 1. Okay, 0, 1. It gets closer and closer, but never gets there. But from this direction, it goes down infinitely, and so the curve is going upward like that, terminating right there just short of 0. Now, if you did the rectangular equation, it would show you the whole parabola on both sides. you have to stop it there. X has to be greater than 0. That's how you express your domain of your X. Where in the world is my pen? There it is. Okay. This is how you stop it there and say X has to be greater than 0. This is to indicate there's any problem with that. Well, I can't find my pen again. Where is it? Oh, it's up there. Okay. This is your, that by itself wouldn't like there's a problem, but it is because you can't go past that. All right, I think that finished there. Now, we will start next time with example 3, not on the slide set, but that's where we'll begin, and we'll go from there. Let's see what homework exercises you have. We almost finished 10-2, believe it or not. Do any of the odds 5 through 21. They're all at Calc Chat, 13's at Calc View. Any of the odds 23 through 33. They're all at Calc Chat, 25's at Calc View. It says you might need a graphing utility for some of those. And say again? The homework is on 707. Okay, and then I think you can do any of the odds 35 to 37. They're all at Calc Chat. And let's see, eliminating a parameter, you should be able to do 39 or 41. They should both be at Calc Chat. And hold off there and we'll pick up from there. So end at 41 and we'll go from there. All right, good deal. Any questions? Okay, so what we'll do, I'll stop the sharing right now. I'm sick and tired of sharing. Okay, and unless there's other questions, we'll end the meeting for everybody. So take care. We'll see you on Wednesday. Any last thoughts, parts, questions, parting shots?
I got the test to work.
You did?
I got it to work.
Did you get it on the other one? On the...
No, I got it through the assignment thing.
Yeah, you did? Okay. Do you know what you did differently?
It was not working with my phone, and so I just had to get things set up on my computer a little bit differently.
I see. Okay, so you don't need it in PDF form.
Nope, I'm good.
Everybody was able to access it? All right, good deal. Thanks for telling me. Saves me a little bit of a problem, but not a big issue, but makes it life a little easier. Okay, take care. We'll see you on Wednesday morning, okay, or afternoon. See you then. Bye-bye.